Okay, we're going to start today with an exponential function. And what exactly is it? Well, it's simply when you have a constant raised to a variable. So if we looked at the definition of an exponential, it would look something like this. A function that was a constant, we'll call it a, raised to a variable, call it x. So a to the x is our exponential function. The constant a has to be greater than 0 by definition, and we don't want a to equal 1 because it's simply, if you had 1 to the x, remember, is always equal to 1, and well, that's just not very interesting. That's a constant function, not a true exponential function. So we have this exponential function, a to the x. The a is going to be some number like 2, 3, 4, so on and so forth. It can be fractionals, things like that. But whatever it is, a is called the base of the exponential, and x, of course, is called the exponent. So there's a couple of vocabulary for you. The x in the exponent, the variable, can be any real number. Okay, so we can raise it to all kinds of strange things, including negatives, irrationals, anything at all. All right, let's talk about what it means now to actually have an exponent in the variable. Well, simply, the easiest thing to do is to just evaluate this function. If I said f of x, and I'll pick a value for a, the most basic one we usually pick is 2 to the x. And we could simply evaluate this when x is some number. Maybe it'll be 3/2 this time. And like we always do, we make the substitution x is 3/2. We can evaluate this on your calculator with that caret button. So you would simply enter 2 caret. Be careful to use the parentheses, 3 divided by 2, and then you can enter. And you should get a number for this. I don't have my calculator with me, so let's talk about what happens when you get the graph of this. Okay, in order to make our graph, we are going to start by using a table of values to help us understand what this graph will look like and understand some of the features of it. So if I'm graphing, and I start with my table, some x values, and I'm going to have y values 2 to the x. Okay, back to that very basic exponential function, 2 to the x. And I'll pick some values for x like -3, -2, -1, 0, 1, and 2. Gives me a little variety. And if I evaluate 2 to the -3, remember, a negative exponent means take reciprocal. So this is the same as 1 over 2 cubed, which of course is 1 over 8. So the first ordered pair would be -3, 1, 8. Then if I evaluate 2 to the -2, remember to take reciprocal, 1 over 2 squared, so that's 1 over 4. And I can keep going. 2 to the -1 is the simplest, 1 over 2. 2 to the 0, remember anything to a 0 power is always 1. Okay, so that's going to be really important to us. And then of course 2 to the 1 is simply 2, and 2 squared is 4. So you kind of see how this is got some symmetry. I'm not going to name that symmetry, but it's got some pattern going on here. So let's take a look at coordinate axes, where I've got the x horizontal and the y vertical. And I'm going to start graphing this. When x is -3, I've got 1/8, so that's close to 0. When x is -2, I'm just a little bit more. Then when x is -1, I'm 1/2. So it's sort of setting my scale. Here's my 1. And I have a point there at 0, 1. And then when x is 1, I'm at 2. And when x is 2, I'm at 4. So way up here. Alright, let's draw a line, connect our dots. This is a continuous function. No jumps or gaps. And you'll notice some key features about this graph, and I'll be referring to those key features all the time. First, notice you have right here a y-intercept, 0, 1 y-intercept. Okay? Also notice that you have a horizontal asymptote right here on the x-axis. And you can think about it this way. If you had, let's say you had 2 to the negative large number, so we're talking about the left end behavior, well, that would be 1 over 2 to the large. So that would be 1 over a very large number, which will get very, very small, but it will never be 0. So that's really our definition of a horizontal asymptote. So what we have is y equals 0 is a horizontal asymptote. And that's a key feature of this graph. Where is that horizontal asymptote? Will be a common question that you're going to get. Alright, but let's make sure we look at the right-hand behavior and make sure we understand what's happening here. When x gets very large, so over on the right-hand side of your graph, as x gets very large, you're taking 2 to the very large value, which just gets really large. Okay, and there's no stopping it, there's no more asymptotes on the right. So it just keeps increasing forever and ever. There is no more asymptote on the right. A lot of kids will want to look at this and think that there's a vertical asymptote. It seems to look like that, but it doesn't. It's actually going to increase forever and ever. Okay? So, don't even think about it. These right here are your 2 key features. So what happens if you take a different constant? So maybe you had 4 to the x. Not really sure why I put that there. Okay. So I changed the base of this exponential from a 2 to a 4, and I just want to see what change that makes to that graph I had before. So I'll do the same thing. I'll do a table of values, -2, 3, -2, -1, 0, 1, and 2. Why don't you go ahead and take a minute and fill in the rest of the chart yourself just to make sure you're good on that part, and I'll be right back. Okay, so you see the values I got from my table, and I've got those points, and I want to put it on the same graph as the 2 to the x graph. So I've recreated it, and I'm going to put 4 to the x on here. At -3, I'm really much smaller than it had been. Same thing. At -2, -1 is only a fourth. It's hard to show. But what's interesting is here at 0, I'm back to 0, 1. Okay, so that's really cool. But then again, when x is 1, I'm above. That used to be 2, remember? And so now I'm all the way up at 4 already. And then, of course, after that, I'm going to be off my scale. So the picture for the new exponential 4 to the x is passing through that same y-intercept, but a little bit steeper here where I just finished, and a little bit flatter. Okay, so similar to when we used higher exponents to graph x squares compared to x to the 4th or x to the 6th, things got steeper and flatter. And they're doing the same thing here by changing that constant base. So this is the new graph 4 to the x. So you can see it still has those 2 key features though. It still has 0, 1 as a y-intercept, and it still has y equals 0 as a horizontal asymptote. And those 2 key features did not change. Alright, so what happens to some other things we could do to this? Well, we could try a table of values, x, and y is equal to a number less than 1, remember, because it could be anything from 0 and greater, with the only exception of couldn't equal 1 for a base. So let's take a fraction to the x power and see what happens. This is really the same as saying 2 to the negative x. Because remember, a negative exponent says take a reciprocal, and that's what we've got. And if you look at it this way, you have that same base 2, but this time it's raised to a negative x. Well, we know that when x goes to a negative x in our other graphs, that was a reflection across which axis? Do you remember? That would have been across the y-axis. So I could actually go ahead and graph this pretty quickly. If this is 2 to the x, can we try that again? Then if I reflect this across the y-axis, then my new graph looks like this. So this would be 2 to the minus x. Just a reflection. Look, it still has this point right here, 0, 1 as a y-intercept. And look, it still has y equals 0 for that horizontal asymptote. Pretty cool. And I'll leave it to you to fill in the chart of values. So I think in the end what we're going to do is call y equal 2 to the x a parent function, and we can talk about all kinds of transformations. So let me look at this again one more time. That's a graph of 2 to the x. Looking more closely, again I still have the 0, 1 y-intercept. I still have the y equals 0 horizontal asymptote. Let's talk about domain. X can be any real number whatsoever, so minus infinity to infinity for a domain. The range is more interesting. Anything greater than 0, so the range would be 0 to infinity. It is an always increasing function. So increasing on the interval from minus infinity to infinity. And it's a continuous function. No holes, no jumps, no gaps. And what else is interesting is it passes both the vertical line test and the horizontal line test, so it's what we call, remember, the one-to-one function. So that's going to be interesting to us later on when we talk about the inverse function, because remember, to have an inverse function means you have to be a one-to-one function yourself. So indeed, this will have an inverse function. So let's talk about transformations in general. This is old story. If you wanted to graph y is equal to 3 to the x plus 1, what do you think is going to happen? Well, I think the x is not a plain old x anymore. It's an x plus 1, which is very familiar to us as a left 1 unit. So I could graph this, and the 3 makes things a little steeper, a little flatter, but that's not going to show up quite as easily. But I can go ahead and graph this. I'm going to go to the left one. So it used to be this point right here, 0, 1, is now this point over here, negative 1, 1. Going to the left will not do anything to my horizontal asymptote, right? You can move that horizontal line left or right, and it's still y equals 0. So that didn't change. And I come right up here. I go through the point minus 1, 1, and I have a horizontal asymptote, y equals 0. And those are the 2 key features I need in order to graph it. We'll worry a little bit later about finding the value of the new y-intercept, but for now I think that's a really nice way to just make a sketch of what we got. When we try another one, I'll let you try it and get back to you. Try y equals 5 to the x, and then minus 2. Give it a try, I'll be right back. Okay, so I looked at this and the 5 makes things a little steeper, flatter, not a big deal. The x doesn't change, so there's no shift left or right, but there is the minus 2, which is obviously a downshift vertical shift 2. So I took everything down 2, which means I also have to take that asymptote. That horizontal asymptote is going to shift down 2 units. So now the horizontal asymptote's at y equal -2. When I moved the old y-intercept from its point 0, 1, if I move it down 2, I'm at 0, -1. And then draw the curve. And you got it. Alright, let's talk about what we can do with this function. The first thing we're going to do is called the one-to-one property. And it's an important property, and it's pretty easy. If I say a to the x is equal to a to the y, then this is if and only if. So remember, that's what happens when you have a biconditional. So this is going to work both ways. If and only if x is equal to y. So, I mean, it's pretty simple. If I had 2 squared is equal to 2 to the y, then guess what? Y is equal to 2. So you can do a lot with this. You can do more complicated equations, but the important thing to remember whenever you do this one-to-one property is your bases must agree, okay? That's the first thing. You're going to get in trouble if you don't have your bases to be the same. It's a on both sides. So for example, what if I had 25 is equal to 5 to the x minus 4? Okay? Well, the bases don't agree. On the left I have 25 to the 1 power, and on the right I have a 5 to its exponent. So let's change the 25. I can call that a 5 squared. So that's going to equal 5 to the x minus 4. And from this, using the one-to-one property, it's easy to see. 2 is equal to x minus 4, and of course, x equals 6. Alright, why don't you try one of these? Remember, it's important to get the bases the same first. Why don't you try 1/3 to the x power is equal to 9. Give it a go. Okay, so hopefully this is how you did it the same way. I get x equal -2. Don't forget, negative exponents take a reciprocal. I have one more for you to try. I'm going to let you try 16 to the x is equal to 1/4. Go ahead and give it a try. I'll be right back. Okay, there's my solution. I get x as -1/2. Take a look. I was a little more careful this time to show 16 as 4 squared. In a parentheses is then raised to the x power, but of course an exponent raised to an exponent is multiplication, so that's what I did. Alright, last thing real quick. I want to talk about what's called the natural base. You're going to see this a lot. It comes up. And I'll leave it as a demonstration in class of how we actually come up with this number. But for now, there is this number. We're going to give it a name, like pi has a name because it's such a special number. And this one is approximately 2.71828, and it goes on in a non-repeating forever fashion. It's an irrational number, just like pi is an irrational number. So when you graph it, it would graph somewhere between 2 to the x and 3 to the x. But you can find this on your calculator. You may have wondered what that button was for. Why don't you go ahead and try it on your calculator and evaluate what is e to the 1 on your calculator. So you'll find the e button. You'll hit 1, and then you hit enter. And you should get 2.71828, and on and on and on. Try another one, e to the -0.3. Be careful you're using a negative and not a minus sign. Try that on your calculator. When you get it, I got 0.7408. All right, see you in class.